I'm starting the stream. Hello, been a while. Welcome back. Oh, that's been completely the wrong place. There we go. Hello, welcome back. This is going to be Chill Maths again. My name's James. I've got some maths. The plan is to sort of chill, I guess. This is what we're going to do on Twitch. Hello, Herb and Maths2222. Number theory today, I think. Let's update the what. I wonder what what says. What were we doing last time? If I do the what command, exclamation mark what in chat, doesn't do anything. I think CloudBot's got bored of us as well. Let's fix that. Where did I go for this? I go over here. So sometimes if I don't stream for too many weeks, the auto mod thing, which also means we're susceptible to the thing that prevents bots. Not currently activated. It's right. Okay, we're on. Da 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 da. Oh, check your mobile phone. A code's been sent to your mobile phone. No, I don't want this. This doesn't look great. Oh, right, the battle is on to try and reconnect this. How's everyone doing? I hope you're well. He says, frantically setting up the stream while the stream's live. That one. Probably that one. Hello, Mary. Am I also muted? That would be fun, wouldn't it? Would mean we get to start again. Yeah, I think it was the twins problem last time. That was the suggestion in chat anyway. Activate. Active. Okay. I think we're now protected. Or whatever. Do we also get was? So I'll try it. Hi, Mary, as well. Hope everyone's doing well. See if I can do this. Maybe that'll update it. There we go. We did it. Welcome back. This is Chill Maths. It's a show on Twitch where we just do some stuff. I think previously on the show we've talked about quadratic residues. We've talked about squaring numbers modulo a prime, and I've seen this fact, which maybe I've seen before, I even have streamed it before for all I know, but I've seen this fact about powers of numbers modulo a prime, so I think we're going to do that. Yeah, I am protected now. I am now. You're allowed to say it all as one word, but you can't put a space in the middle. Good, right, okay. Long-running joke that Mary is a bot, so we have to train the Mary AI to get around the bot protection that we've got. Right, because we like this bot. Okay, right. Here's powers of a number. So I tried to do this in Desmos. I've discovered a sort of problem with doing this in Desmos, which I might try and work my way around, where we've got some Desmos people in chat, so we will see. Yeah, I was thinking about something like that, but no, it didn't quite work, did it? Okay. So Desmos lets you do the remainder when you divide. So quick recap for people who haven't seen this before. 10 is a multiple of 3. No, 10 is a multiple of 2. 10 is one more than a multiple of 3. The way Desmos treats that is like this, to say when you divide 10 by 3, the remainder is 1. This is quite good. It's not amazing. I want to do powers of numbers like this. And it's not true that 19 to the power of 13 is 29. So I've run into this problem with large numbers quite quickly. If I set my slide, I've got these sliders, look. If I set them to large, then I get this kind of grid of what the powers are, but it's not correct. It's got these zeros at the bottom where it thinks that certain things might be multiples of 29. They're just definitely not. 29's prime, 19's prime. It's not a multiple of 29. The problem is that this number is huge, and I think Desmos is losing precision in a way which means that it can't actually do this. Which means it's not using a kind of clever method to do this. It's just calculating a to the k and then taking the remainder. So up here I've got, these are my coordinates for the points. I'm looking at some number along the x-axis. Along the x-axis. Some number a, and we're looking at powers modulo some number n, in this case 29. And I was hoping to look at this and look for patterns, but I can't do that if some of them are wrong. So I think we're going to write our own mod power function thing. Possibly using recursion? Possibly using recursion. Yes. So the proper way to do this, if you want to actually work out the remainder when 19 to the power of 13 is divided by 29, is something like build up from small powers and build your way up to 19 to the power of 13, maybe one at a time. We could do something really clever with binary. There's this trick that people would use using binary, where you use the fact that 19 is 16 plus 2 plus 1. So then if you can work out... No, you use the fact that 13 is 8 plus 4 plus 1. So then if you can work out 19 to the 1, 19 to the 4, and 19 to the 8, you can just multiply those together as a kind of shortcut. Rather than working out 19 to the 7, 19 to the 8, 19 to the 9, 19 to the 10 in between. And you pick those powers of 2 because you can work those out quickly by squaring. Not immediately, but by squaring. We're not going to teach Desmos to do that. I think I need to teach Desmos how to do... Yeah, so let's do powers correctly. So I'm going to define a function. It's going to take two inputs, a, and the number that you're taking a to the power of in order to do a to the k. And the correct way that I'm going to do this is something like, if k is 1, just return mod... Oh no, it's going to be a function of three things because I need the number n in there as well. We need to do modulo some number n. Okay, so my function is going to be, if k is 1, then just return... This is going to be... add a comment. I found out you can add comments, so I'm going to do that. F-A-K-N is a to the k. Oh, come on, typing a to the k mod n. It's gone really dark. Things that are going to be adverse. Oh, did I say something other than 18 when I should have said 18? Was it the powers of 2? It's probably the powers of 2, wasn't it? Things are going to be adverse today. It's dark, it's raining. Oh, those are fine, those are happening outside. We can overcome those. Okay, so if k is 1, I just want to see the number... Oh, maybe it's more natural to do. If k is 0, I just want to see the number 1 for the power. However large the number is, I just want to see the number 1. I think this is how you do cases. Hello, Moon Machine Rex. Oh, is it meant to be 18? I've got no idea. We're going to find out. I'm going to get Desmos to calculate it for me. I can't quite remember how to do cases, so I'm going to have a quick go over here. Is it this? It's something like this. Yeah, okay, so it's that. If not, then it's the other one. If not, then give me a k minus 1 mod n times a for another go round. Multiply the previous one by a and do that mod n. That should be good. And then it'll keep going down. It'll reduce the power of k one by one as it goes through each time, multiply by a each time, and then it'll get back to 1. So I shouldn't use f for everything, should I? So let's check this by doing some powers of... Well, the easiest thing to do is to do powers of 1. Doesn't like that at all. Doesn't understand full stop. If I got a full stop in here somewhere by mistake. Oh yeah, instead of a comma. There we go. Good. Right, so 1 to the power of anything is always 1 mod anything. This is not a great test. The test is probably going to be something like... if I put 1 here, it's doing everything mod 1. If I put 100 here, then it should return powers of 2 until we get large enough that it's doing powers like 256, 512, but this is good enough that it can do enormous powers of 2 and still get me back to like the last 2 digits of 2 to the 100 by just doing sort of multiplying 1 at a time. I'm aware that putting the backlight on now makes me look like I'm sitting in weirdly shadowy darkness, which I don't love. Well, it's a math stream, isn't it? It's not a glamour shoot. There's other streams for that. Right, let's do 19 to the power of 13 mod 29 using this. And I'm sort of hoping that I get 18 because that's what maths 222 said in chat. Well, I've got 3. So now I'm going to go to a different source of truth, which is Wolfram Alpha. I'm going to plug it in there. It's chill maths, isn't it? It's chill. It's just chill. Right, let's see what Wolfram Alpha thinks. Should I do different smaller powers of 19? Oh, I don't even know. No, it's hard to work out. 19 squared is 361. Is 361 really 13 more than a multiple of 29? Take off the 13, 350, 348. Is that a multiple of 29? 290 plus an extra 58. Yes, that's the last one I'm doing in my head. I think Wolfram Alpha is quite good at powers. I think it does something clever. Is it going to give me 3? Ah, good. Okay, so I'm now quite happy with my code. 19 to 13. Good. Oh no. What has happened here? Someone's used extra characters. That's a disaster. How am I going to... Oh, it's got a like hat on the E and a dash after the word viewers. It's a disaster. There's no way I can filter this. Right, let's at least ban them just because I've got to send a message. Alright, good. That'll teach them. Oh, I'm really upset. I'm going to assume that they started doing that precisely because we started banning the word viewers. That what we're seeing is a response to the meta that we created. I think we did that. Yeah. Oh, you did 19 to 23. Oh, that's the one that's on screen. Sorry. There you go. That'll be why. I agree. 18. Right. I do need a mod, don't I? Problem is on my streaming schedule is very infrequent and inconsistent. It was not your fault. You attracted your right cakes. Right. Yeah, I don't know Python. You may have spotted from previous attempts at doing Python code on stream. But I think if Python doesn't have POW... Oh no, it does, doesn't it? It has asterisk asterisk. I don't know what that does. Hello, Football Stream. Good to see you. You're slightly cropped off the text box there. What have I done? Why has that happened? Oh, am I going to fix this live? This is going to be the stream where I fix stuff. I can't even find the bit that does that. Oh, Twitch chat. Right, and then up. There we go. It's a bit better. The top's going off the chat, but that's all right. Good. Football Stream, everyone. Right, okay. What am I doing? I'm going to replace Desmos's mod calculation, which, fair enough, combined with Desmos's large number calculation, doesn't give me great results. I'm going to replace this with my a to the power of k mod n code, and now we get a structure. That's more like it. Now we get some stuff. Okay, everyone watching, you're looking at a blob for each power that it's possible to calculate mod 29. So each column, meaning left to right, is the number that's being raised to some power, and as you raise it to different powers you get different remainders sometimes. I mean, not if the number was 1. If the number was 1, then whatever power you raise it to, you always get 1. So this column's only got a dot down here. And if the number is 28, well, 28 in the mod 29 world, 28 plays the kind of role of -1 because it's 1 less than 29. Multiplication respects kind of multiples of 29. It kind of all works out in a nice way that because 28 is 1 less than 29, it really is like -1 when it comes to calculating powers. So then what I was going to say is that you get this kind of -1 effect where 28 to the power of 1 gives you 28, which is a bit like -1 to the power of 1 gives you -1, but then to the power of 2, power of 3, and backwards are just flip-flops between these 2 points. And then in between there's loads of other stuff, which we can now actually look at, because I think we've now got this working. It's nowhere near as symmetric or pretty as I thought. I mean, it's good. There's a lot going on. So I've got 2 sliders here. One of them is just n, which I guess we'll set to something like this. One of them is n, And one of them is B, which is the kind of, what if I set B to? No, B is kind of the maximum power that we're using. So that I can do this, which is to animate it nice and slow. So to start off with, if you only look at the first powers, you get just a linear thing. If B is 2, then you get this kind of quadratic on here. We looked at these before. I think they're kind of like, some of them look a bit like Space Invaders. They tend to have this loop bit in the middle that looks like a parabola. Very symmetric because it's an even power. That does follow. And then as we increase B, well, let's animate it. As we increase B, it puts more and more spots in. But not in a way that's easy to understand. All FurboStream is training a neural net model. Good luck. And you would like more RAM. I've heard there are websites where you can just download that, so maybe keep an eye out for those. Right, what do we have noticed? What do we observe? As always with these things, so there's sort of almost left-right symmetry, isn't there? There's these points, like here and here. What am I looking at here? This is the number 12. Only has kind of 4 things that you see. So the powers of 12. There's a concept called order that we're going to talk about in a second, I think. But if I just look at 12, there's 12. Ooh, I've got an idea. I'm going to clone this and kind of highlight my favourite number in a different colour. For just 12, sort of pick out that one. I'm only going to do that in like highlight. How large are those points? 20. There you go, that's cute. Now I can just look at 12. For technical rendering reasons, I'm going to set this to 21. And I can look at just 12 and see that the powers of 12, you get a second thing, then you get a third thing, then you get a fourth thing, but the fourth thing is 1. So 12 to the 4, oh goodness me, sorry, 12 to the 4 mod 29 is just 1. And after that, you multiply by 12 again, you go back to 12. It kind of loops. This is a concept called order, where after a while you have to get back to where you started because there's not that many places to go. The world of remainders is a pretty finite world. After a while you have to get back to where you were, and the amount of time that it takes before that happens for the first time is called the order. And some of these are very quick, so we saw that this 28 thing happened really quickly. So I highlight the 28s. Oh, I've got highlighting technology now, look. They tick tock backwards and forwards, so then there's no new dots as we fill in everything else. And some of them take ages, like 19. And I know 19 takes ages because look, it's filled up the whole column. So if I animate this, it does 19 squared, 19 cubed, 19 to the 4, 19 to the 5, 19 to the 6. These are all different as it keeps multiplying by, in that case, 19 each time. And that reveals a kind of surprising fact, which is, oh, it's coming back down again. Surprising, oh, there's a cliffhanger, look. That reveals a kind of surprising fact that in the mod 29 world, we're all just powers of 19. The powers of 19 fill up everything, except 0, right? But the whole number remainders, mod 29, here they are in a column, are one-to-one relationship with small powers of 19. The word for this is that 19 generates the group of units under multiplication. There are other generators as well, so 2 is maybe the more obvious one over here. This column is full as well, so we can play this game over here where as you go you gain a new orange dot every time as it sort of fills up the column. And you can see that there's some, that was the Windows disconnect noise, I wonder what that was. Was it the stream? No. There's some obvious questions you could ask, sort of. Which numbers are the generators? Well, 29. I can see a few of them in these kind of columns that are formed. You could ask about why there aren't any filled up rows, I guess. Rows are different to think about, aren't they? You could ask what happens for other primes. You can ask whether 2 is always a generator. And some of these questions are really, really hard. You could ask if there's always a generator. I think that's a question that I'd like to learn about later in the stream. Got this half plan. I found some notes about this. We've tried this before on the stream to look at some number theory notes and learn some number theory. I found that I'm better at it if I've got some motivation from sort of looking at things and gaining some intuition first, so that I've got something visual in mind when I'm reading the number theory. Which is why I built this Desmos thing, and then found out that Desmos can't do powers, and then found out that Desmos can do powers if you teach it how to work them out slowly and carefully. I feel like I'm telling it off there, slowly and carefully, one at a time. This is probably quite bad for me, isn't it? That it's doing recursion all the way down for every single point, for every single. It's fine. It's fine. What is it? 30, 30, 30. It's a few thousand. I'm a mathematician, not a computer scientist. If my computer blows up, it's the computer's fault. Right, okay. We can do this for other powers as well, or other primes. So this is 31. Oh, just that animation is so fun. Whoop. There we go. So here 2 is not a generator because, did you see it hit this number 1 too early? It went 1, 2, 3, 4, 5, and then 2 to the 5. 2 to the 5 is 1 mod 31, which is not surprising because you know the number 32 is a power of 2. And then as you put more powers in, you get, well, not a full column over here, but there are quite a few other full columns on there. For example, the 3 column is full. Hang on, I just, I reached for the thing and it wasn't there, which means I need to make the slider. It's going to go from 1 to n-1, steps in size 1, it's grabbable, and it's the name of this. Yes! Oh, there we go. I love Desmos so much. It's so easy to build a kind of tool that you then have as like a UI element. It's just so, I don't know. I know anybody who knows about computers who's watching says, oh, this is easy, you do this. There's a Python library that just does it, but no, for me, it's just, you label it and it just comes up. You can select which column you want. There's one. What is that then? 17. You just read it off. Yeah, so the theorem that I'd like to build towards is that you can always find a column. You see, because I want to talk about findings. It's like moving left and right. You can always find a column for any prime which is filled, and that's a hard thing to prove, I think, but kind of maybe within reach that we can maybe understand the proof if we really try. It's non-constructive. It does not tell me where to put this slider in terms of n, that nobody knows what function I'm supposed to type here in terms of n. I guess this is, n's kind of the main thing, isn't it? Let's sort this out a little bit, sorry. B is how many we're looking at. You're going to calculate all of them. F is very important, it can go up here. There's a comment, always comment your code. Yeah, so there's nobody knows a function that you can put here. That means that you always get to see the highlighted column. The proof's not constructive. Yes, so we're going to find the order, and if the order is p minus 1, or I guess in this one n minus 1, one less than the prime, then it goes around everywhere. That's what we'd like. We'd like the order to be p minus 1 so that we get this kind of highlighted column effect. Let's pick another prime to look at. I should probably label this, shouldn't I? Hang on, let's add a note. A is a prime number. Now I'm doing notes. maximum power to show. We've got F. Good. Easily the most comments I've ever put on any code. I'm a mathematician. That's just slander, isn't it? 37 is a good prime. So then the challenge is to find a column. I can't actually see a column anymore. Ooh, is 37 prime? Yes. 39 is famously not prime. What have I done? Oh, I'm not doing enough powers. I'm not doing enough powers. I kind of want, this is nice for the animation, but it's annoying that it doesn't. There we go. You've got to fill it all the way up to show all of the powers. Then you will find a column. That was 13. 15. You're making a neural net with no comments. Hashtag no comment. I guess my intuition at this point is that there's some pattern to these generators. There's some weird stuff going on in between that I can't explain at all. Like, why is it like this over here, but not over here? I guess some of the powers are odd, some of the powers are even. If we only look at the even powers, it will probably be nice and symmetric. Odd powers don't have that reflection or symmetry, whereas the generators kind of do. If this is a generator, then so is P minus this. That sounds like the sort of thing that we can prove. If some number generates all of the remainders, then putting a minus sign in front of it can't hurt. Putting a minus sign because, again, 32, 5 less than 37, plays the role of minus 5 in this 137 world. I put it up to 37. Did I say I was doing that? I put it up to 37. Sounds like the sort of thing we could prove, I guess. I guess it's probably relevant that 37 is odd. Let's see what we can do here. Can I get a whiteboard? It's my favourite bit of the live stream, is where we sort of notice a pattern and then try and prove it. It's pure maths. So let's go. Where are we? We're over here. Has this board already got anything on it? I'm going to regret putting on screen. No, we're good. It's already got stuff on it that I don't regret putting on screen. Okay. And then, right, okay. Ready. Some people say I should set this up before the stream starts. Yeah. Oh, it wants me to update this as well. No, never. What is this then? This is sort of a claim, I suppose. Not proved yet. If A... So these are the powers. Are all different mod P. P prime. Then so are, and then I want the powers of minus A. And we might need to use some facts about, I'm going to ambitiously write the word proof here, we might need to use some facts about multiplication. Best part is 32 min. What have I done? Unless you don't want tea. Oh, I've got 32 minutes. Yeah, okay, until 3 o'clock, right? 3 o'clock's when we take a tea break, he says, already drinking tea. See, now the top of chat, I've ruined that. Because now the top of chat is off the top of chat. I'm going to go nudge it slightly down. I don't know what it is about today, but I think I might have ruined it in the way it was originally broken, but there you go. I don't know what it is about today, but I want to fiddle with all of the settings and things. Right. Okay. So we're going to go for an ambitious, just try and prove it without thinking. My thought is basically that the minus signs don't hurt, and whether or not there's extra minus signs will all be okay. It's not a very fleshed out thought. Okay. Here we go then. If minus a to the I and minus a to the j are equal mod p, with, I suppose, I and j are supposed to be not the same as each other and between 1 and p minus 1, then I do love an if-then structure. Oh, right, okay, so hang on. If I and j have the same parity, then the minus signs just cancel. We've got the same number of minus signs. And we get a to the I mod p. Contradiction, that's the only thing that we assumed up here. The powers would have to be the same. Powers of A, and A is a generator, so they're all different. If they're opposite parity, now where on earth am I going to go with this? This is not immediately a contradiction. So what's the problem with this? Oh, so this says that, what does this say? It says that a to the j minus I is surprisingly minus 1 mod p. And I say surprising because then, no, this looks possible, doesn't it? That could be minus 1, and then it will do all of the others. Maybe this is not true. Let's try some other primes. My new thing is, this is enough to change my opinion, I think, that possibly this is just wrong, and it's not the case. It's true, so 5, and there's a couple over here, and then 4 in the middle, but maybe we got lucky for 37. Maybe I should try a prime like 31. We kind of already had 31, didn't we? Oh yeah, and it's not true for 31. That's really that's good. Okay, phew. It's just nonsense. Good stuff. Yeah, so here there's a generator 3, and then 31 take away 3 will be 28, but that's missing half of them, which can happen, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 ish. Half of them ish. Yeah, half of them. Okay, good. Worth it, I think. Spot a symmetry, try to prove it's there, realise you can't immediately prove it, think, maybe it's not true. It's not true. Good. Okay. Some people would clock that down as a terribly embarrassing failure because I tried to prove something that isn't true. Haha, I'm smiling though, because that's how learning works. You've got to find. Let's go. It's not really emote shaped, is it? It's not really emote shaped. Let's isolate. It's a bit small. Isolate. I think that's pretty hard, actually. There we go. Take your screenshot now. We isolated it. Ding. Right, we'll use that. Okay. Math Tutor 2 has also got that worked out. Order. They've done order. Oh, you're calculating order. You doing it just, yeah, I thought so. There'll be one of these. You're going to work out when it happens. If you get 0, then stop. No, this is your calculating powers. And then, oh my goodness. Yeah, you're going to work out when it's 1. Ugh. This is great having Maths Tutor 2 in chat. Maths Tutor 2 in chat is better at Desmos than me. I did not know it had indexing. Cool. Good. Okay. So this sort of thing makes us cautious, I think, or makes me cautious. That putting in a massive prime, I realise that I don't have anything that says. Well, at the moment we haven't talked about anything for what the generator might be. Oh, does someone want to explain RFL? Go on, chat. Explain RFL. It's an emote we used to celebrate. It's good news. Okay, right. I think I've now built up enough appetite to actually look at some number theory. So I think I'll be brave and I'll look at some number theory notes. I'll show you why. I've got these notes. How do I get these on screen? Yeah, back. I have a few weeks off, and then I think I'll just do all of the different things, at once. You know, bit of Miro, bit of Desmos, bit of screen sharing this, switch to the other device, so that we can write on lecture notes. You know, just a bit of everything. Is that going to work? It's not amazing. There we go, perfect. Cool. So I found these notes by Keith Conrad. That, oh my goodness, I can't resize that one without resizing this one. Sometimes I just can't. Oh, and I can't move it either. And now it's gone. Where's it gone? Okay. So it's going to link that window to this window. So I'm going to resize that one. Some people say I should sort this out before I go live. Make two windows, and then moving the left one shrinks the right hand one. So I have to sort that one out first. There are two linked windows, and moving that one moves that. I've never seen that before. Whoa. Did anyone explain RFL? RFL's from the Natural Number Game, which is an online game where you have to construct the natural numbers from raw axioms of mathematics. Oh, there you go. There, Herb's got the law. Anyway, right, here's some notes from Keith Conrad that I found online about powers. And section 6 says, for some moduli m, there is a unit. No, wait. This is good news, I think. There is a unit whose order is blah, blah, blah. Its powers fill up all of the units. In context here, units are the things that are co-prime. And if we're talking about primes, then we're good. It's what we want. Yes, here it is. It's theorem 6.3 that I would like to understand today, if I can. When p is a prime, there is a unit mod p with order p minus 1, but it's a non-constructive proof. Just to read out some of the stuff that's on screen that makes me pause. It's used in crypto systems. You can find it with brute force search in log p time if you believe in the generalized Riemann hypothesis. So, you know, wow. Okay. Just a bit of maths going on. So my plan to understand this is that it's in this PDF. It's on page 10 of a PDF, so we stand a chance, right? It's not buried in sort of months of number theory where we'll never get to the bottom of it. It's on page 10. I reckon we can do that. I had a look through the first few pages. Ignore that big exclamation mark. First few pages, not too bad. So we're going to go back and have a look at some of that. So this is exploring powers and thinking about units. It's making heavy use of sort of something called Euler's theorem, which says that, well, it's a generalization of Fermat's Little theorem, if you know that one, for a prime, that a to the power of p minus 1 is congruent to 1 mod p whenever a and p are coprime. So if you have some number and you raise it to this very large power, p minus 1, you always get something that's one more than a multiple of p. That's Fermat's Little theorem. And then Euler's theorem is a bit better. It says that it generalizes this to say that if A is congruent to N, I need to put this disclaimer in Fermat's Little theorem to make it clearer what the difference is. If P is prime up in this one. That's grabbed the wrong window. There we go. If P is prime, then you get to say this stuff up here. Euler's theorem doesn't have that restriction. It just looks, but it changes the power to be phi of n. So Euler's totient function, which is the number of things coprime to n in the set 1 up to n. So not counting n then. Right. There was a coloured bead proof story for Fermat's Little theorem on Maths Club, which was very good. That was Jonah, I think. Jonah came on and explained that if you have A colours of bead and you're trying to make a loop with beads on it, which might be one of A colours, the number of beads being P, then the kind of naive way to count those is to say, well, there are P things, each of which could be one of A colours. So you get A choices, then A choices, then A choices, then A choices, then A choices. Sort of A to the power of P. But lots of them can be rotated to give kind of other ones. And you can put them in these groups of 5. If P is 5, put them in these groups of 5 to sort of connect them up, except for some odd ones out. It's a good proof, which I've bottled it by not doing all of the proof. But yeah, right. Good. Okay, so we got some notes that make heavy use of Euler's theorem and have some stuff about what this has got to do with working out recurring decimals. If you care, when you work out a decimal for a fraction, like here I'm doing 1/7, you're doing division and you're carrying over a remainder, and each time that's a bit like, you take the remainder and you write it in front of a 0, that's like multiplying by 10, and you take the remainder mod 7 or whatever, because you divide by 7 and write down the remainder. So the operations you're doing there are multiply by a number, in this case 10, and then take a remainder with respect to a different number and continue that process until you get back. So that's exactly what we were just getting Desmos to do, except with the number 10 instead of, well, anything else. So only doing powers of 10. So in Desmos, if I do powers of 10, is this true? Yes. The number of things in this column is the number of digits in the decimal expansion of 1 over that number. Yes, 1 over that number. So if I set it to something tiny like 5? No, not 5. I'm possibly out by 1. Or even 2. What am I doing? Or does this not work when less than 10? Whatever. What am I doing? Am I out by 1? Has 19 got an 18-digit fraction? Maybe it does. 18 has got a 1 digit? Something seriously wrong. If I'm claiming that 18 has got no, it does. It's all 5s. Believe the maths, eh? It's all 5s. Get stuck. I can't see the ones at the bottom as well. Yeah, I need to allow for the fact that my slider thing is hiding any multiples, which can happen if this thing's not prime. Okay. So sometimes 10's a generator, and sometimes not. If 10's a generator, then it fills up the column, and you get the kind of maximal possible length of decimal expansion for that fraction. Sometimes it doesn't quite work out like that. So the order here is a little bit smaller, which is why this doesn't have 30. You can't see it anyway because 30 digits is too many for Desmos. But this doesn't have 30 digits before it repeats. It starts repeating earlier. That's the link. Yeah, the others are if you use different bases. Yeah, so we like base 10, but the mathematics, if you were working in a different base, you would be looking at different. Let's go that down. There we go. If you're working in a different base, then it just changes the number 10. So in particular, you might be interested in binary, and you might be looking at the length, how long it takes for numbers to repeat when you write out their binary expansions for fractions. I don't know how to do that in Desmos, but I can just point this slider at 2 and tell you that that's what you're trying to count. And 2 is sometimes a generator, I think. There's a theorem about that. That was sort of supposed to be foreshadowing, but I couldn't quite play it off as. Oh, what an interesting question to think of. Is this the theory? I think nobody knows. Let's actually look it up. What am I even Googling? Something like, is 2 a generator for infinitely many groups? I think it's not known. Anyway, never mind. For infinitely many primes or something. We'll get there when we get there. Yes. Right, okay. What are we counting? We're counting something, aren't we? Yeah, okay, so there's some stuff in here about powers and order that I read through the other day. And I was thinking about generators while I was reading it, so I've scribbled some notes on it that mostly say generator, question mark. So in here, they've worked out the powers mod 7 and spotted that you can get all of the different numbers of the rainbow before you get back to 1 if you do powers of 5. Or powers of 3. This has got sort of everything going on. And there's some maths on the next page or two about how these things get into a repeating cycle, and that repeating cycle has some period. Because we know from Euler's theorem something about the columns here, that when you do a power of every 6, every 12, because that's a power of 6 times a power of 6, or 18, because, well, FLT says that a to the power of p minus 1, which in this case is 6, is congruent to a 1 mod p. So if we're thinking about the prime 7, then powers of 6 we never get back to 1s. So there's some sort of common sense proofs in this section to talk about how the period of the sequence has to be a factor of 6. Because it's got to hit 1 when it gets to 6 every time it gets to 6. I'm gonna try and bluster that as the kind of fact that we don't memorize the proof for. We just think, yeah, it's got to divide it. There is a complicated proof on this page, which we are not going to worry too much about. And then there's some stuff about powers where, yeah, orders of powers. This one, section 3, which is asking us to think about what's the order of the power of a power a to the k, like this. So if you know the order of a, maybe you know it's a generator, and you want to know whether a to the k is also a generator. The fact is that if they're co-prime, then it's the same order. If not, you should divide by the highest common factor. And I sort of want to brush that as common sense as well, but I think that's a bit of a stretch. So let's see if I can turn this into a kind of question about just repeating sequences or something. Yeah, so Lagrange's theorem is about, there's a way to prove these things with Lagrange's theorem, right? Which is to say that if you're saying Lagrange's theorem to mean that, what about raising something to the power of the size of the group? That's a good way to prove FLT and Euler's theorem at the same time, by considering the group of units modulo n, The size of that group is phi of n by definition, and Lagrange applies to that group, tells you that anything to the power of the size of the group gets you back to the identity, or the order of the group. The order of the element divides the order of the group. Right, maybe I should read the proof of theorem 3.2. I think it's important. We'll have a quick look at it. It's almost time for a cup of tea, I think. We've done some exploring, we've built some Desmos, we've taught Desmos to do powers, we've spotted that you sometimes get generators. We know where we're going. We're trying to build up to the fact that for any prime, there is a number that generates that. That the prime group's always cyclic. It's a good fact. I would like that fact in my back pocket. It's kind of fact to get out. Yeah, okay, I've convinced myself I would like to know the thing that's in section 6. This is section 3. On page 4, we've got 6 pages to go. Hour and 10 minutes. Right, okay, we're going to read this, I think. So let T be the order of a to the k. So this is supposed to be 1, and T is supposed to be minimal because it's the order. We want to show that if T is n over k, we want to show that T is n over k if k divides n. It's right. T is n if right. Okay, sorry. This is 3 separate things. We want to show that if k divides n, then it's just this. If they're co-prime, then it's just n, and that in general, we want to show this, right? I know what they're doing, but that's what we want to show eventually. I don't mind too much about the 2 stepping stones. Cool, right, now let's do the 2 stepping stones. Part 1, we assume that k divides n. They build up. It includes the first 2 special cases, but they're worth knowing on their own. Okay. Right, the structure. The condition, this, is the same as a to the kt is 1 mod m. So let n, are we working mod m everywhere? Yes. So n divides kt by theorem 2.1. Oh, I hate it when they do this. I just find these so hard to follow as well. Right, no, concentrate. Alright, so A has order n. A has order n. So n divides kt as a to the kt is an example of something that's 1 mod m. If you have an example where something gives you 1, and you know that it's sort of periodic sequence with period n, then whenever you see something which has got back round to 1 again, you say, well, that was a multiple of the period, wasn't it? The sequence was periodic. And you sort of press the button kt times. That must be a multiple of n because it's a periodic thing that gets back to 1 every n. Right, good. AKA theorem 2.1. See, it's so hard, isn't it? So difficult. Okay, n is less than or equal to kt, so n over k is less than or equal to t. We also have the reverse inequality. Oh, good, okay. Since this a to the k to the power of n over k, so we're just checking that n over k is the right answer in this case, aren't we? Then you get a to the n, which is 1, because n is the order of a again. It's less than or equal to n over k by definition of what the order of a unit is. And this is an example, so t has to be less than or equal to this. I think t has to divide n over k in the same way that n has to divide kt, and that works out as saying, right, that they're all equal to each other. Good. Okay. Oh my goodness. Right, okay. I'm happy with this, I think. Your power can be raised. Your power can be raised. N over k is what you might guess, because you have a to the k, a power of a, and you want to try and get 1. You know at the back of your mind that a to the n is 1, so you might try n over k. But what if it's a bit less than that? Well, the reason it can't be less than that is that if a to the kt was 1, then that would itself be a power of a. So kt would have to be less than or equal to n, bigger than n. Almost nailed it. Not quite. Yep, okay. Good, part 2. I'm going to get to the bottom of this page, I think. Going to get to the bottom of this page. Then, cup of tea. Oh, I want to show that this has order n. If they're coprime. Right, here's the equation. It's the same as a to the kt is 1 mod m. So n divides this, same thing again. Oh, and now I'm nervous. But n and k are relatively prime. So n divides t, so n is less or equal to t. What are we hoping for? We're hoping that we get to divide by the highest common factor of n and k. The reverse inequality too, a to the k n is this. Oh, if you raise it to the power of n, you get this. Hi, Rice Cooker Man. Doing more number theory. We're looking at powers of numbers modulo other numbers. There's a lot of numbers going on. That's what makes it number theory. But we're going to take a quick break in about 5 minutes when I get to the end of this page, understanding the order of the power of an element, which feels like it's pretty sensible, but I'm checking to see if there's any tricks. I will let you know if I find any tricks. What's this? T is less than or equal to n because if you raise this thing to the power of n, you get back to, this is clever, you get back to 1 anyway. Is this always true? Yes. This is always true, isn't it? If you take your power that you're interested in and raise it to the power of n, then you can always do this power rearranging thing, which will give you 1, which means that you can only make the order less by taking a power of a. You're playing with something which eventually, after n applications, will get back to 1 anyway, whatever you picked. Multiples of things. In this case, that is in fact where we are. Yes, you don't. If the common factor is 1, we're good. Right, general case. Let's go. Here we go. General case. For each k bigger than or equal to 1, we want to show that this, you just take n and divide it by the common factor. Congruence is the same as this, which is the same as n divides kt. My theorem 2.1 n, we're now practiced. N is the order of a, and this is an example where a has been raised as a power and given us 1. It's a periodic sequence with period n, so we get back to 1 after applying some multiple of n multiplications of a. T is the smallest positive integer such that n divides kt. Yeah, because it's the smallest possible period. If you had a smaller one, then this would also be true. This is going to be the smallest number that does this. Necessarily all of the ones that do this? Is the other way obvious? Yeah, maybe. I'll do the soap film question in a second. Factor k and n of both k and n. Oh my goodness. Yeah, okay. So factor it out to get k prime and n prime, because you factored out the same thing. Factoring out the same thing from each. Then these things are coprime because you've taken out their common factor. So n divides this. So then here it is. Here's the common factor coming out both sides. So n prime divides k prime t, and these are now coprime. So n prime divides t. n prime is less than or equal to t. This is pretty similar. Yeah. Reverse inequality 2, and here's the clever bit. A to the k to the n prime is a to the k n prime, which is a to the n k prime. T time. We got to the end of the page, which is a to the n k prime, which is 1 to the k prime, which is very clever. The exclamation mark, both products are k and divided by the common factor. So that's, I think, the key thing is to consider a to the power of k n over the common factor, which is an integer. On the one hand, it's an integer multiple of k, which is interesting because that's the number we're interested in, which is and on the other hand, it's an integer multiple of n. So you're going to get 1. I think that's pretty good. Okay. Don't really understand why it's the smallest. I think I accept that it does this. So why can't you make t smaller? That was the previous part. Right. We'll grab some t in a second. Why was t smaller? Why can't you make t smaller? Oh yeah, I didn't really believe this. Didn't really believe this part. Or really, this line here. So that's the one I need to think about, possibly. So as you're calculating powers of a to the k, the first time you see this is the smallest number. But what if you had a smaller number? So a smaller number that gave you a multiple of n up here would then just give you 1. So if you find the smallest number, yes, okay. Giving you the order is the same. Right, okay. And then we get that, so we get this kind of order. So if A has order k mod m, no, if A has order n, come on, if A has order n mod n, then a to the k has order n divided by highest common factor modulo m. Cool, okay, seems like a good place to break for a cup of tea. I'm going to take a break just to refill this mug, and I will see you back in a couple of minutes. Thanks for watching, and thank you, Mary, for redeeming the tea time thing. I'm also going to run an advert for 1.5 minutes. If you see an advert, then you're supporting charity, rather indirectly, but you're supporting charity. Any proceeds from the stream go to charity. Right, good. Okay, see you on the other side of an ad break. Be right back. Welcome back. Thanks to Herb, who subscribed to the channel the moment I left the room, which fair enough, I guess. But thanks for using Prime subscription on this Twitch channel. If you don't know, then if you have Amazon Prime, you get a free Twitch subscription. Subscribing gets you animated versions of some of the emotes to use, I think, anywhere on Twitch. So make the most of that. Good. And you did it while watching 4 or 5 adverts back to back to back to back. So there you go. Yeah, welcome back everyone. Good. This reminds me to do shout-outs for the surprisingly large number of people who followed me during my 3-week break. Thanks for the follow. You Lemon, Bogger_0, RO Darkfire, PXX49, Felix EDK, and Crackerjack404. I love the way that people's usernames work on this website. It's just a full mix of word phrases, numbers, and everything else. Yeah, good. Right, yeah, we had a few weeks off. Good. Okay, so then this is just a table of. Here we are. I thought while I was getting a drink, I thought about this result because it's almost not used any facts about powers or modular arithmetic, really. Like, what did we use? We did all this sort of messing around with multiples of things going on, but we haven't used Euler anywhere. Have we? No, we haven't used Euler. It's just a fact about periodic sequences. So we've used the fact that a to the n having order n has some meaning. But I feel like you can reinterpret this just in terms of periodic sequences. You don't need Fermat's Little theorem or anything in here. You need to be able to exchange the order of powers over here. Sort of says that these things have to. What's that called? If you have sequences and you join them together, then taking sequences of length n, sequences of length k. You can concatenate them into some long sequence, but if it's the same length, then that's the sequence. I think there might be a way to explain this in terms of sort of wallpaper or something. You have a roll of wallpaper and you want to know, or some sort of stamper, or some sort of print making thing. And you build yourself a mega print making thing which contains. So sort of like we're imagining some sort of stamp art stream. Let's go. Some sort of stamp with, I don't know, like this, and you stamp it, blam, and it gives you a kind of stamped image. And then maybe you build yourself a kind of, which has got some length or something, some integer number length, like some width in pixels or something. Then you can, do other stuff as well. Megalomorph in chat agrees, hooray. Basic things in groups. I think even more basic than that. I'm going to try and explain it with stamps. Let's see if this works. So then if you build yourself a kind of mega stamp device out of several of these. Is this what I'm doing? I'm imagining this periodic sequence being that you use the stamper. Is this right? No, this is not really right. Maybe it is. No, yeah, the periodic stamper is not quite this. Because in my analogy, the pixel width of this, the integers come from something else. Okay, maybe not stampers. Yeah, there's a stamp that's been going left to right. That has changed colour from subscribing, which is exciting. So, good times. Twitch. Okay, periodic sequences. I might need to give this a think, but something like I need a kind of go-to periodic sequence or something. It's tricky because all the things I can think of are factors. Right. Okay. Something like you have a sequence going on, and you take 3 terms of the sequence. That's still sequences. Instead of just looking at each term of the sequence, and you look at the period of that. No. Rubbish. Good. Okay, here's a table in case you need it of 12 divided by the highest common factor of k and 12. Okay, I think I'm going to skip this section about applications. It is nice. There's this application that is on screen at the moment. Take a screenshot now or try and find these notes by Keith Conrad if you want to see it again later. The only consecutive powers of 2 and 3, so 2 to the m, 3 to the n, only differ by 1 in these cases and no other cases, which is kind of nice. So looking at small m first and then looking at large m. No, wait, looking at large m afterwards, everything goes wrong. And in this case, it does something by orders. I read this before, I thought it was fine. And there's something down here about whether 2 to the n is 1 mod n, which is nice. Okay. And I didn't understand this the last time I read it, so it gets a question mark in the margin, so I don't know what's going on here. Oh yeah, there's some idea. For each a greater than 2, there are infinitely many n for which a to the n is 1 mod n. This confused me a lot. And the idea is to use, and then these, and then I thought, oh goodness me, to put these numbers n as the powers inside here. I thought, oh goodness me. Yeah, I decided I did not understand this. It's something like FLT might be relevant, right? Because this is a to the something, but maybe not. I did not feel like I understood this part, but never mind. And then there's a bit about periodic decimal expansions, which we're skipping, but it's cool. It's cool, but we're skipping it. Past 10. That's not how you do live streams, is it? You're not supposed to skip this. Cool, never mind. I'm on a mission. I want to try and understand this thing that's in section 6. And there's lots of kind of treating things carefully in here, which I was not doing earlier. But I'm enthused to know that whatever 239 I have a nice short decimal expansion. And here it is being calculated. I'm multiplying top and bottom by 10 to the 7 minus 1. Good. Decimal period length is 7. These initial zeros are interesting. I guess for a large enough number, if you're looking mod n with something very large, then you could get... It could do a kind of Pollard row thing, right? Where it could be eventually periodic. Could that happen? Yes, that could happen. Are there infinitely many powers of 2 that end in 32? Probably not, but there is at least one because 32 does it. Yeah, let's set this to like mod 100 or something. If you set this to mod 100, it'll tell us the last 2 digits of... Oh, now I've annoyed it. If we set this to 100, it should tell us the last 2 digits of prime powers. I think it's doing it. It might not be doing it. I've really annoyed it. It didn't update straight away, and I'm scared. Sorry, computer. I don't know if I should save or not. Let me reload. Cool. Okay, right. Yeah, the trick there is don't save and reload so that you get back to your kind of save state before you messed up. It's like Dark Souls but for Desmos. You realise you're in trouble, quickly reload. Right. Here's the thing that Math2222 said about other bases. Massive arrow, other bases. There's some binary stuff. Right, how much do I need? Section 5. Oh, I'm a fake gamer. I don't actually play games. I just talk about games a lot. That's how you get kicked off Twitch, isn't it? I'm only good at really easy games. There we go. That'll save me, won't it? That'll be good. So order of products, because order of products is different from just thinking about orders of powers. Because when we're doing orders of powers, there's only one thing that's happening, really. A to the k is just lots of multiples of a, plomp, plomp, plomp. Eventually you'll get back around again. For a product, I don't know. And this seems good for relatively prime orders. Right, I need to decide whether or not I need to read this theorem. Watch me bailing out of that Dark Souls reference. Lightning speed. That could be my speed running. Regret. How soon after saying something can a live streamer realise that they shouldn't have said it? No, I'm probably not even the fastest at that. There's probably some good examples of streamers regretting saying things quite quickly. Streamers, very remorseful. Right. Mouse was on screen there as well. Good times. Okay, fine. I will think about trying an actually difficult game. Right. Okay, do I need this? So it's like theorem 5.2, and then the bit that I skim read but wasn't concentrating, put a big exclamation mark next to it, which is my code for I don't understand what's going on here at all. Come back and read it another time. Here we are, another time, and I'm skipping it again. A to the k. I don't want any of this, do I? Do I need this for section 6? Here's section 6 with little stars and happy faces. The thing I want to understand. How much do I need this? Oh, I don't like it when lecture notes do this. They say why in brackets to prompt you, the reader, to actually think about what's going on. And I don't like that because it's so obviously good for me. It's like being reminded to brush your teeth. It's like, oh yeah, okay. Good, right. What are we doing down here? Can anyone see a 5 point somewhere on the screen for what we're going to need? Not yet, I think. No known algorithm for finding a generator of this that's substantially faster than brute force search. Okay. This is classic Euler maths, apparently, and Legendre as well. And then Gauss does it better by classifying all M of the following form. Okay, and I feel like we've seen these cases before. We had a brave attempt at reading some lecture notes about number theory, not just 12 pages, but we had a sort of attempt at looking at some number theory lecture notes, and I reckon we saw these numbers before. 2 for p to the k, 2 times p to the k. I can't remember what was going on there. It was something to do with quadratic residues or quadratic forms or something. Occasions where it was relevant for an n squared plus 1 problem or something like that. Good-o. Right. We're now ready to prove theorem 6.3, allegedly, although we did skip all of section 5. We're having a look to see what we need. Forwards and backwards, isn't it? What can we see? We can see step 1 on screen. Oh my goodness. Yep, great. We're going to factorise some polynomials. Step 2, step 3. From step 2. Oh no. 5.5 tells us that we need to do this. And then we're done. So we do need to know 5.5. Let's read. The reading is easy. There's the end. Okay, we are going to need 5.5. What's the structure here? Ah, so this is sort of step and then proof of each of the steps. I wrote that one in. Let's write this one in here. Bullet points. Each one comes with its own little proof. There is an integer mod p that has order p-1. Okay, we're going to read this bit, and then we're going to read this bit, and then we're going to work backwards, then we're going to go back to 5.5. We're doing a sort of forwards and backwards approach today. Is each integer, other than these ones, a generator for infinitely many primes p? That would be nice. I kind of want it to be a generator for all of the primes p, and I'm greedy like that, but no. And also this is unknown, this is a conjecture. It's called Artin's primitive root conjecture, and it would follow from generalised Riemann hypothesis, which would be nice, but you know, there we go. And I think that's where these lecture notes stop, so I think this is sort of the point of this. Okay. So this is the thing I want to understand, that the multiplicative group modulo p of units mod p is generated by some element of the cyclic group. Is this in the classification of groups or something? Where have I seen these numbers? A separate question. What was the context where I saw these numbers before? It was a number theory course, I think, so possibly it was the same fact. The trivial context of exactly the same thing. Groundhog Day, seeing it all again. You never know. Right, so what's this going to say? So last step, let's see if we can understand it backwards. That seems like a challenge worth doing. So factorise p-1. By step 3, there is a unit AI mod p with order each of these things. Ooh, and then you can just take the product of those things. So find something with order qi to the ei, and then just multiply them and use a big fact from section 5 to say you just multiply them, and possibly because these things are co-prime, it all works out. You get an element of order p-1. That feels a bit constructive, because in that last step it just says to multiply them. I bet the step 4 is non-constructive. Let's read step 3. So step 3 is hopefully going to tell me, in order to connect to this, it's going to tell me how to find something of order qi to the ei. My plan is going to be to multiply these together while we're working mod p. Step 3. For each prime power q to the e that divides p-1, so this is my qi e to the I example, there is a unit mod p of order q to the e. That's what I want. Good. Proof that an order has order q to the e is the same as this. Oh yuck. A to the q to the e is 1 mod p. Ugh. Order q to the e. And I really do want that, because maybe p-1 is multiple of 4 or something, and then I do want to write 2 squared or something in here. Having order p-1. Yeah, p is prime. p-1, not prime. Even. Great. So we've got to deal with this q to the e up here. And this thing, q to the... Oh, e-1 up here, so q before was not. This means a mod p is a root of... Now, I don't know what this is because I'm reading the proof backwards. But I can see something up here about polynomials factorising or something. It's not a root of this. Okay, so we'll show that this has a root that is not a root of that. From step 2, so this is how it's going to connect to step 2, where you take the degree to be this. I'm guessing it's a degree, and n is p-1. So I hope there's a d and an n up there somewhere. T to the p-1 minus 1 is divisible by t to the q to the e, because q to the e is 1 mod p. Q to the e is a factor of p-1. This is going to say something like you can factorise this polynomial in that way that we sometimes do, by taking out a factor like that. I hope. Since this is a product of all of those roots by step 1, if you say so. Oh, right, because polynomial factorisation or something, you know where the roots are. Everything does that. That's Euler's theorem. I guess in this case it's Fermat's Little theorem. Any monic factor of that leading coefficient 1, I can remember what words mean, must be a product of some of those linear factors. Whoa. Yep, okay. Unique factorization. So maybe we need to go and study the entire course, rings and modules, to remember why this thing has unique factorization. So this has q to the e distinct roots. Oh, what? And loads of them. Oh, q to the e is quite small. Q to the e is smaller than p minus 1 because it's a factor of p minus 1. By similar reasoning, q to this has a q to the e minus 1 distinct roots in z over p. In order to get your roots, you have to just take some of the factors from the available factors. If you're going to be a factor of that. Yeah, so I need to see step 2 to explain why this polynomial divides it, and then you just pick off some of the factors, and you get more of them when you take a larger factor. So there is at least one of them that has this. Actually, probably quite a lot, but hey, and not a root of that. If I justify probably quite a lot, not really. I don't understand what's going on because I need to read steps. I think it's steps 1 and 2 we're going to do together. Just to piece together what the idea is polynomial factorization. Here's a polynomial, t to the p minus 1 minus 1 is this, because Fermat's little theorem tells us that all of these are roots in the polynomial ring. This thing is divisible by these linear factors are pairwise relatively prime. P is prime, and so it factorizes just like this with some quotient over here. Repeating the degree shows that that's just a constant. Leading coefficients, yeah, it just tells you that you've got enough t's on the right hand side. So we'll factorise this nice and carefully. We are now going as fast as possible. We are now speed running to get out of this proof, because I want to go back and understand section 5.5, because I think the key part of this proof is going to be you can treat each of the prime factors separately, and I guess there's a question for what you do for each prime factor, which is something to do with consider the polynomial, consider what its roots are, where you choose the polynomial quite carefully, but the kind of more important thing seems to be going back to looking at why the kind of core of this is going to be the non-constructive. No, this is going to give us this is the non-constructive bit of the proof. The bit that says that this polynomial factorizes, and in order to make a polynomial of a large degree, you have to take some of the factors, but we don't know which ones. I'm doing my best. I wish I could do this well. Also, hi Unstucky, how are you doing? You alright? Are you streaming later today? I've seen you're streaming at the moment sometimes. I forgot to ask Phobos Stream if they're streaming later. We will find out. Okay, what are we doing? Not a sleepy you, that's pretty good. We take that. What are you going to do with your newfound awakenedness? Awakenedness? That's not a word. Oh. Consciousness? That's probably the best I can do. What are you going to do with your newfound consciousness? No, that sounds insulting. Undetermined for Phobos. Also hi. Okay. Cool. Unstucky's going to stream later, maybe a bit. Enlightenment's no. See, the thing I'm trying to avoid is words that sound like you were incorrect before, and words that sound like you were tired before. We need this because this is a thing. But if you're kind of tired all the time, then having a moment where you suddenly have like, maybe I could get something done. I guess I'm also separately joking about the idea that you have to be productive in your moment of not being tired. I've made too much out of a single thing that you put in chat. Hey, welcome to Twitch. D and n are positive integers with d defines n, then these polynomials, one divides the other. This feels like the sort of thing we say, doesn't it? With polynomial division. Yeah, so this is like this is going to be nothing to do with modular arithmetic, right? But just like if you see this, because it's going to be sums of the other ones, right? If you try and divide it, let's put a larger number up here, like 36 or something. We kind of know what the quotient is. Yeah, it's this. There it is. The sum of all of these other things. It's d prime n over d, yeah. So just multiply by the sum. And then when you multiply, if you were to multiply this by t to the d minus 1, you would get n up here, because you multiply that by, what am I saying? Yeah, it's a substitution. If you multiply this by t, then you get almost the same polynomial. T minus 1, you multiply this by t minus 1, and multiply by t increases all of the powers. Multiplying by -1 doesn't change the powers, but does put a minus sign at the front of each term, so almost everything cancels. Fair enough. And subbing in t to the d. Yeah, okay, so if you think about this as my favourite trick, which is to rewrite a polynomial using lower powers by using some sort of substitution. Yeah, can I do that in terms of roots of polynomials? So then you see that x cubed equals 1 is a root, and that's also a root over here. Might be relying on unique factorization in order to pull that off in terms of, or the factor theorem, I guess. Yeah, I think I might be relying on some sort of fundamental theorem of algebra, factor theorem sort of combination to say, well, if you plug x cubed, if x cubed is equal to 1, then this thing is also equal to 1, so you're all good. Any root that satisfies this satisfies that, and then in order to turn that into a factorization fact, I think I'm relying on the fact that I haven't missed any factors, and I do get all the factors. One of those is easy, and there's something like the factor theorem, the other one is hard, and there's something like fundamental theorem of algebra, I think. Let's do it this way, which is to explicitly write down the quotient, but for some reason out by a factor of, this is very upsetting to me, this is out by a factor of d, because they've done the substitution. If you're going to write out an explicit expression, we could just write out, this in terms of t to the d, right? With an extra factor of d, because then it would be t to the n minus d plus t to the n minus 2d plus t to the d plus 1. If n is multiple of d, then it goes down until you get down to t to the d plus t to the 0. That's not that hard to write out. I just think that would be anyway. Explicitly, that's the quotient. Good, okay. So this step is easy. This is a step about polynomial division, hiding in the middle of these number theory lecture notes or wherever I got this from. Okay, so we've got a fact about polynomial division if d divides n. We've got some sort of understanding of what the roots are for this polynomial, which I think is reliant on how factorization works for polynomials mod p, which makes me a bit nervous because I can't remember most of that maths, but sure, I'll take it on faith. And then let's look at step 3 again. So down here, step 3 asks us to consider the polynomials t to the q to the e and t to the q to the e minus 1. The idea is that this has got higher degrees, so it's got more roots. And you can't just say that higher degree polynomials have more roots. You have to have some idea about what the roots are, otherwise it could be lots of repeated roots, couldn't it? But here we know what the roots are. The roots are, these things are both factors of t to the p minus 1 minus 1. That's kind of our n. Where does it say that? It says that in here somewhere. I remember n being p minus 1. There it is. These are both factors of p minus 1, and we know all the roots of that. So the factors of this, unique factorization applies. The factors of this don't have any repeated factors in. Nothing goes wrong, in a way. You get bigger degree, you get more roots. So there's a lesson here to think about. There's a lesson here for me, which is to think, if you have a fact where you would like to show that something is true for all a, or there is an a that does it, finding a value of a that does that is a solution to a polynomial question. And understanding the polynomial is key. So maybe that's my motivation separately. We've talked a bit about motivation earlier. Maybe this is my motivation to go back to the polynomials over rings lecture notes that I've looked at before and think, yeah, okay, I care about solving equations with whole numbers. And solving equations with whole numbers, you can turn those into asking about roots of polynomials over ring of integers mod p. And over that ring, being able to factorise the polynomial would be good, because we know that once you factorise the polynomial, if you have unique factorisation, you can say quite a lot about what's going on. Megalomorph, no, sorry, that's a bit before my time. I was an undergrad at Cambridge, but about 7 years after that. I have doppelgangers everywhere. Dispersed them to do my bidding. Would it be my bidding? I'm the youngest one. Maybe I'm doing their bidding. Good information, thank you. You've made me rethink that whole relationship. No, there's the other doppelgangers out there doing other stuff. And I'm the one stuck here on Twitch, doing maths. Right, Megalomorph is another Cambridge person. Yeah, what's the other one doing? What are they up to? I mean, I know from the Doppelganger network, but I want Megalomorph to tell me something important, probably. Were they Spider-Man? Did they play Spider-Man in that one movie? Anyway, never mind. Okay, so we take this number that satisfies this polynomial, that's a root of the equation, and then we use that. It's in context, that means that it has order q to the e? Oh, because the order must be a factor of this. Order must be a factor of this. If you see... Yeah, the order must be a factor of that, and the factors are just powers of q to the e. That's why we're looking at separate factors. So maybe this is some sort of pretender. Maybe the order could have been that, but no, that was a different polynomial. Oh no! The other James Monroe who's doing MathSoc at Warwick is no longer doing MathSoc at Warwick. Ah, that's a shame. I mean, that's fine, obviously, but it means I never got round to getting in touch with the other person who's at James Monroe doing maths at a UK university. Oh no. Probably don't know. Okay. Yeah, Herb's got the animated emote. Oh, I should have left that one to Herb. You have the animated emote now. There you go. What a great advert for Amazon Prime usage of emotes. Anyway, we have a hole in our proof at the moment, or a hole in our understanding of the proof. A hole in my understanding of the proof, and because I skipped 5.5, and 5.5 tells me why we can take these different elements with order like this and just multiply them together, and that will be good. I can sort of see it, you know, that if you have this element and this one or this one, it repeats. If you just multiply it on its own, it repeats every so often, and this one separately repeats every so often at a completely different amount of time. So if one of them says I've got order 4, so every 4 times you multiply this together, you'll go back. And the other one says I've got order 49, then, well, if you want to get both of those things to line up, then you need the same product. Those things are co-prime. But there's probably more to it to say why do you want both of those numbers to line up? How do you know that? It's going to be because it's a factor of the thing, right? It's going to be just because it's a factor of the thing. Oh, somebody's made the cow. Somebody's made the cow sphere. I've seen this GIF before. Has it turned up in chat as well? Is that one of yours? That's one of yours. Well done. Good use of that GIF. I'm assuming it's one of yours because the code is Megalo27cow, which, if your emotes work like mine, then they've taken the first certain number of lessons of your username and then stuck a number on the end, which is also how some people's usernames work. Used to stream. Right, good. Okay. Well, yeah. It's very good. Sorry, I've still got it on screen. It's a little cow turning into a sphere. Right, okay, what are we doing? 5.5. I think we've got to do it. We can skip some of these examples. Look, example 5.8. Oh, it is 5.5 that has the... Oh no, 5.6 is the one with a big exclamation mark for... Oh, I'll come back to this. Induct on... these things stay relatively prime. Yeah, this is not exciting, is it? So it's actually the thing before that we need to read. Pairwise relatively prime, then you're fine because the product so far stays relatively prime. Yep, okay, so this is going to just tell us for 2. Yeah, if they're coprime, then their product has the order that you want. So this is the thing that's standing between us and understanding theorem 5.2 and its proof. Okay, so for units with relatively prime orders, the order of their product is the product of their orders. Oh, that is very good. I like that. I'm going to say that again. The order of their product is the product of their orders. Chat is now going to work out the genus of a cow, which, good luck. Sort of biology question, and it's some facts about cows are relevant. Cows have 4 stomachs. That one's not relevant. Okay. Is this proof going to have the same shape as the other ones? Is it going to tell me that the order is greater than and less than something? No, the shape of it is going to be more or less. Okay. What's n? Right, let's start at the top. Since this works, right? You can, if this one takes n1, so it goes round to get back to 1, and that one takes n2. Then after n1, n2, well, that is a multiple of both n1 and it's a multiple of n2. So both of those things will have worked. Using the fact that multiplication is commutative quite a lot. Good news, we're not over a general group, we're in an abelian group, so we're all okay. This fact is sort of seriously not true for non-abelian groups, is it? Anyway, never mind, don't think about non-abelian groups. Don't think about groups, think about numbers. What's a group? Let n be the order of this, what m? In particular, this thing's supposed to be 1. So obviously it has to divide n1, n2, because we just saw that was an example. So if n is the order, it has to divide n1, n2. And I think this is going to be effort to show, yes, the other way round, that these things both divide n. Already showed that, yep. Okay, right, so work then to show that n1 divides n. I already used the fact they're coprime. So we know that this thing is 1 because after n applications, the definition of the order, you're supposed to get back again. So raising both sides to the power of n2, oh, that's good. That's a clever trick because n2 kills off a2 when you raise this thing to the power of n2. You'll get back to 1. So you've got one sequence that repeats every n1. You've got another sequence that repeats every n2. They're coprime, and you want to find some multiple of those. You want to find some number, which is the period of sort of stamping each of the stamps separately. Yeah, this is a bit like those polyrhythms. If you've seen these videos of drummers on TikTok or whatever, where they've got to drum one pattern with one hand and drum a different pattern with the other hand, and they pick coprime numbers, and it takes a long time for those things to line up again because they go through all of them. Is it a bit like that? There's a timing issue there, that they're doing fractions of a unit rather than doing integers, but I think it's the same in the end. If you hit on every third beat versus hitting on every quarter beat, then or quarter of a bar, or whatever they're doing. Quarter of a bar versus a third of a bar. 4/3 polyrhythm. I think the result here is that those things, something about 12, you take the product because they're coprime. Something like that. Yeah, but they're using fractions. So what? What am I saying? So you do a rhythm where it's every... Yes, it's sort of a rhythm where it's every 3 somethings, and a rhythm where it's every 4 somethings. Will take 12 somethings to come back again, but that's not how they talk about it at all. They say not clever things, like 1/12 of a bar or something. That's not how they say it. Yeah, and then you can combine lots of them together. What is going on there? So for those, I would just say something like you put them over a common fraction, and the denominator is the product because they're coprime, and the smallest one is, yeah, then they're not. The smallest numerators coprime to each other, so you can't do better than that. Something like that. Where here, what are we going to say? Do n2 times, and that will get you down to this. So n1. Well, you must be happy now. Secretly, that's because there's an extra factor of n2 in here. But you must be happy now. And n2 wasn't the thing that sort of fixed this. Excuse me. Yeah, there's the presence of 12, right? But to explain it, you have to bring in these numbers 3/12 and 4/12, which is not really how they start, is it? They start by thinking about 1/3 and 1/4, I think. Third time, and triplets versus quarters. So then you write those over a common denominator, which will be the product. Yeah, I guess this is the result. But you write these over a common denominator, which will be the product. So 4/12 and 3/12. Write them over a common denominator, which will be the product. It takes a hold. This is stupid because you know from the start, for the drumming question, you know from the start what the period is. Because your plan is to repeat it every bar. It's a repetitive exercise. So you sort of start from knowing the period, and then the question is kind of what's the largest integer that you could, what's the smallest integer that you could split this down into to describe the pattern as either beats on that point or not. It's just a complicated way of saying, it's complicated. Yeah, something like this. Is a common denominator to analyse these rhythms or something, and the common denominator is just the products. I guess the fact that it doesn't line up halfway through is kind of what we're talking about. So showing here that it will come back when you do, in this case, 12. No, yeah. If you do 12, then that's a multiple of 4 and a multiple of 3, so you're back to where you started. Yeah, but I was thinking about doing not quarters, but 4s. Then, relative to, once you know the answer is 12, you can divide everything by 12 and fit it in a bar, and that's your polyrhythm. But, Ooh, maybe we'll have some music recommendation for us that I missed. I missed the comment about pufferfish as well. Wow, chat's going off today. I'm learning so many things. Okay. I was just about to read this, wasn't I? M1 and N2 are coprime, so M1 must divide N when it divides this product, so it's not going to be in there, it's going to be in here. And doing the other way around says that N2 divides N, So, are we good? They're coprime. You need to know this as well. They're coprime, so their product divides n. Yeah, that makes sense, doesn't it? It feels like the sort of thing I'm supposed to know. If B divides A and C divides A, and B and C are coprime. I always have in mind I have unique factorization over the integers, which is not really what's going on here, but is true for integers. Doesn't generalize well, but hey, that's what I have going on in mind. I'm thinking about their prime factors, which is a sort of crutch to lean on, I suppose, to think about things in terms of their prime factorizations, when it's actually something much more basic about what it means to divide, right? Can I prove that? Can I demonstrate that point? 10 minutes on the stream. If B divides A and C divides A, and B and C have highest common factor 1, then what do I actually need, right? Prove that BC divides A. There's probably something clever. There's probably something clever, isn't there? So part of me wants to just write down Bazoo to say that there are m and n such that bn plus cn is 1, and then sort of hope that if I multiply this up correctly, that I can get to BC dividing A. Doesn't seem likely, does it? Yeah, I don't know why have I done this Bazoo step? What am I doing? Oh, this is fun. A little bit of number theory along the side. Maths Studio is going to prove it in terms of lining up. This is what I want. I want it in terms of lining up a rhythm. Maybe not a rhythm, but lining up a pattern. You have two separate patterns, and your operation is to place a row of stickers of length. Yeah, you're trying to every step you place a sticker and you, I don't know, tick a box or something, and every third sticker you're happy, and every other box tick you're happy. It takes you 6 until you're simultaneously happy on both counts. It's the product of 3 and 2. This kind of thing that takes 2 steps and this thing that takes 3 steps line up on the product, and not before. Has to be a multiple of 6, and this argument is to say, if you look at something else, when it comes back. Maybe I should learn to solve a Rubik's Cube. I've been around people who can solve Rubik's Cubes, and they've explained it to me a bit. It seems like you've got to learn a recipe for how to do it, which I've never been bothered to do. I sort of want to... I have this project in mind, right, that I want to solve it without being told how to solve it, and I worry that might be really hard. I have this other story that I learnt to juggle without being told how to juggle. I just tried it until I could do it. And I'd quite like to put Rubik's Cubes on that list, if I'm going to do Rubik's Cubes. I then got advice on juggling and learned some tricks from other people as well. But I learned to juggle by just doing it until I could do it. And sheer bloody mindedness, I'd like to do that with Rubik's Cubes. But I fear that Rubik's Cubes might be too hard and I shouldn't try. Is there going to be a Desmos that tells me how to solve a Rubik's Cube? I hope it is. Or a Desmos implementation of a 3D Rubik's Cube? Yes, it's a 3D Rubik's Cube. That's very nice. Does it solve? It's got a little shadow. This is adorable. And it says 3D Puzzle Cube, but it's actually in Desmos 2D. This is amazing. Did you make this? That's very cute. Oh no, does it shuffle? Oh, it does shuffle. That's really bad. Oh my goodness, and by bad I mean good. Maths 222, did you make this? Oh. In the middle, you can do moves. Oh, I see, right. It doesn't animate, but it does move them. Got order 4. Spin those ones round. Oh, this is terrible. You did make this. Oh my goodness. Why did you do it in Desmos 2D? Maybe does Desmos 3 have the... This is amazing. Yeah, muscle memory. This is terrible. I could lose a lot of time here. Right, okay. I don't think this is going to be high-res to solve Rubik's Cubes, probably, but it's very impressive. Wow, Brian, have you put that in the Discord? You should put that in the Discord. Or on the... I think Reddit would like it. Wow. Is he better at Desmos than me? Okay. Meanwhile, I'm going to try multiplying these small numbers together and see if I can get that right. These things are co-prime by factors. You see, I sort of just want to say they've got different prime factors. I should be better at this though. So A is B times K, and then C times L. These things are co-prime. Remember, try to remember this. Multiply them? No, surely not. No, this is stupid. This is really stupid. Yeah, I've become really stupid. What am I doing? What am I doing? This should just be true by sort of first principle nonsense, right? Or I should just be able to nonsense my way through this. Hang on, so B is A over K. So this shows that BC divides A squared, right? Which is not what I wanted, but shows that BC divides A squared. Then, yeah, not that good. Right, coming back to it. Almost ready to give up. Good. So take these things separately, or something, and then the product of the orders. I'm so cross to myself that I can't even do this little puzzle on the left-hand side. What is going on here? We've got a puzzle. It's chill maths though, so let's not take it too personally. Is it something like take... Can I take my bazoo thing and start multiplying it by these K and L objects? I don't really want to, but maybe I have to. If I multiply it by K... If I multiply it by KL... I'm not very keen. So I multiply by KL, I get some things on the left that look like A. And I get some things that look like rubbish, really. And I get KL on the right, and I don't want to do that. That sounds rubbish. But what else can I do, right? What am I missing? If you've got two factors and they've got no common factor themselves, it's ridiculous. It's got to be a combination of these facts, right? Okay, it's 4 o'clock, but I'm not stopping till I've done this bit. I'm not stopping. Here we go. That's a dangerous claim, isn't it? Why do I say these things? Right, so this product over here is precisely a squared. So I know that BC divides a squared. The problem is that we haven't yet used the fact that B and C are co-prime. Oh dear, haven't yet used the fact that they're co-prime. Over here we know that if B and C are co-prime, does that mean that K and L are co-prime? No, there could be extra factors around that are shared, not in B or C, but just other stuff, making A really large, like there's an extra multiple of 5 or something in there that wasn't present in B or C. So you can't tell me anything about K and L. Why is this hard? B and C have highest common factor 1. Okay, go back to the Bezout fact. That's all I've got, right? Yeah, from first principles, having highest common factor 1, I don't know anything, right? If you see any statement B and C in, then you know they're co-prime. But that's not helpful. Right, so down here, knowing that B and C are co-prime, what does that get me, right? I'm going to start talking about prime factors, but I don't want to talk about prime factors. I want to do it from sort of just facts about divisors, so stuff like Bezout. But if I'm using Bezout, yeah, Bezout's fine. Bezout's pretty primitive, right? Anyway, what am I doing? B divides A. Maybe I do have to multiply this up by K or something. I don't really want to, but multiplied up by K. I sort of did it, but did it really tiny so that I wouldn't really commit to it. So this tells me what, that AM plus CKN is K multiplied by K. Aiming to show that BC divides A. I'm nowhere near that. Nowhere near that. What do I think the answer is? So I think the fact is that if you take BC and multiply by KL over highest common factor of K and L, I think that should just give you A. So it should be the true fact. How am I going to get there? So multiplying up by all the other stuff in some sense. You've overcounted the stuff that's highest common factor. That is my plan. Oh no, this can't be true because then highest common factor of K and L looks like it would have to be A, which is not true at all. What do I think? So take some large number like 36 or something, and then you've got the 3 divides 36 and 4 divides 36. These are separate factors, and you can multiply them to get that 12 divides 36. And 12 divides 36 with sort of, because it's 3 times 4. Well, because the amount you multiply by, you have to multiply up the 4s by nothing you weren't planning to, and the 3s. Hello. You would have to be a factor of AB. Yes. But all the factors of AB have a multiple less than AB, which is not a factor of A or B. Factors of AB. Yeah, so thinking about factors of AB is a good idea. Have a multiple less than AB, which is a factor of A or B. Maybe you mean A and B. Not sure. All factors of AB have a multiple less than AB, which is a factor of A or B. But that means they both have to divide a number smaller than AB. But as they're coprime, that can't happen. Yeah. I like some of that, I think. Yeah. I'm being slow on at least 2 points of your Twitch comment. But that's normal, isn't it? Right, I might have to admit defeat, I think. Just work out the coprime bit. Work out the coprime bit. I can do it. A multiple of A or B at one point in there. You meant A or B. It says A or B. Okay, right, good. I think I'm going to have to ditch this. Why can't I do this? What is wrong with me? Well, never mind. One of those days, isn't it? Right, good. I'm going to call stream there, I think. Thank you for joining in with Chill Maths. Thank you for the Rubik's Cube. Thanks in chat, people who have joined in. Later today, I think Stucky is live, and Fireball stream not live today, but it's sometimes live. So you can follow other cool people who are live more regularly than me. You can find them on Twitch doing maths out there as well. I think I am here next week. So I'll let you know if I get anywhere with this. What an unfortunate note to end the stream on. But hey, I'll let you know if I solve this number theory problem. But I'll see you, I think, next week. Take care, everyone. Bye, Urban Maths and Mary. Right, yes, how do I end the stream? I really can't remember. It's one of these buttons, or it's probably that one marked end. Bye.